Swayam Prabha. Digital India. Educated India.
Today we will discuss about modulation and sidebands. Well, by now I understand you must have got a feel of what the different types of signals are, whether they are stationary, non-stationary, and then how we can distinguish these two just by looking at it in the time domain, but more importantly we can look at them in the frequency domain, know their frequency contents, and then try to characterize the signal. One thing you will realize when we are going to do FFT, we always assume that the signal is stationary, okay. But you know that the process of FFT takes some time. What would happen if the signal was varying the instance you are doing the FFT? So, for example, you are doing a number of FFTs. You have taken the first block of data, and the second block is also being digitized and ready for FFT. But if the you are trying to do, and similarly you will be doing an average FFT, you will be doing a summation of all the FFTs and then dividing it by the number of FFTs, so that you get your averaged FFT. The reason we do this averaging is because to reduce the random noise, okay, and this random noise error will actually reduce by this equation, where n is the number of averages. Okay. This equation comes from the probability theory, and we will not go into details of this, but it suffices to say that once we are doing the FFT of a stationary signal, if I do increase the number of averages, the random noise will be reduced. Okay. So, averaging helps us to improve the signal characteristics or signal features while doing an FFT by removing the random noise. Otherwise, let me just give you an example here, that if you did an FFT of a signal, you will perhaps get a lot of low frequency, high frequency, and this could be because of the random noise present in the signal. This is in function of frequency, this is the amplitude. So, my objective is to reduce this random noise by having more number of averages of this stationary signal. Okay, then I will have a sharp peak, and this is the averaged FFT. Okay. But this is very realistic, very ideal, but what would happen if the machines rotating speed undergoes a change? By change, I mean not that you are running a machine at 1200 RPM, you want to run it at 1600 RPM and so on. No, I am not talking about that. I am talking about, say for example, if you are running at 1200 RPM, because of a power supply variation, because of load variation, which could be intermittent on and off. So, this 1200 RPM will then vary by an amount of delta RPM, very small, it could be 1 or 2 RPM. But what happens if you are taking this data continuously, you had assumed it to be stationary. So, you are violating the definition of stationarity. So, what happens, one average, maybe I will draw them by different lines. These frequencies, once it can be here, another time it will be here, another time it could be here. So, once you have an average of this, you may have a signal something like this, and this is not desired. This is something. So, I cannot identify this frequency of my machinery because of this is because of what is known as signal smearing. Signal smearing has occurred because the signal's frequency has changed while you are doing the FFT or while you are doing the averaging. But if it is a nice constant steady state constant speed machinery, if such averagings are done, then we will not have the problem of signal smearing. To avoid this, sometimes we do what is known as synchronous time averaging or frequency averaging. Once we do that, the spatial variation is reduced, and another method is by having a triggered acquisition. Okay. So, some of the features will be prominent once you do such synchronous time averaging and frequency averaging. Okay. But many a times, even sometimes just a single acquisition is good enough. For example, once the signal is fluctuating quite often. So, we should be able to capture the signal just by taking one block of data, particularly while we are dealing with transients kinds of signal. This happens only once. So, in the next block there may be no signal, previous block there could be no signal. So, in such a case, maybe just one block of data processing is sufficient, particularly once we have such transient signals or for non stationary signals. Okay. Now, here I would like to draw your attention to a signal processing module which we have developed at IIT Kharagpur under the virtual labs program of the Ministry of Human Resource and Development, MHRD. So, I will there is a lab on mechanical systems signal processing, which you can access through my website, www.iitnoise.com. It is linked to this website, and once you go to the student resources, you will click there and I will take you there. Then, because a course on machinery condition and signal processing cannot be just 40 lectures, okay, it has to be also done through some bit of labs. We possibly cannot go to the lab. So, I have tried to bring the lab to this classroom. Okay. So, there are few experiments in this portal where you can do the virtual lab at home at your leisure, and then try to generate signals, try to do their time domain analysis, frequency domain analysis. I will not take it to the detailed exercises in this class, but I will just show you how to access it. So, what you need to do is you can go to this website on iitnoise.com, and this is the address. So, once you come to the student resources, and there is a virtual laboratory in mechanical systems and signal processing. If you click here, it will take to the NPT MHRD website on virtual labs, and this is the lab for mechanical systems and signal processing. In fact, throughout the course of this course, when we are going through the other examples, other lectures, we will come to these experiments one by one. Right now, you can access basics of dynamic signals, basics of frequency domain signal. I mean, the first 4 you could perhaps do right now. I will just show you how to invoke basics of dynamic signals. All you do is click there, and then there is an introduction of understanding about the signals. There is a bit of theory on this topic, and then how you measure all the different time domain parameters, and then you can go to the different modules. There are 3 modules by which you can generate the signal. One is by user defined waveforms, other is by mathematical function, and the last one is your actual measured data. So, then in the user defined waveforms, you could generate a square wave, sine wave, triangular wave, sawtooth wave. You could write your own mathematical expression for the signals. You can add signals, see the beating phenomena, etc., or you may have your own real world data, which you could perhaps bring into these files. So, the module 1, if you go to the simulation, I will just show you the screenshot of this signal. What happens here is, this is the screenshot you will be having. So, you can generate your signal. Right now it is sawtooth. You can change the amplitude, give an offset to the amplitude, change the frequency, see the waveform, and then this program itself will calculate the mean, the maximum, the standard deviation, kurtosis, crest factor, form factor, skewness variation. So, you get a feel of the signal, feature of the signal, just generating yourself, as if you do not need a signal generator or an oscilloscope or a computer to do the analysis. If you go to this website, and next module of course is you could add your own you could generate your own signal, and then you could also see the same effect. And the second experiment is on the responses of first order and second order systems. You need not go through this right now for this course, but the most important for the frequency analysis is you can find out in the third experiment basics of frequency domain signal analysis. You could be finding out the amplitude spectrum, the real imaginary spectrum, power spectrum, power spectral density of any type of signal which you want to give. Similarly, here it could be user defined functions, mathematical function, measured data, and then in fact, this is how the screenshot of the frequency analyzer looks like. Again, here you generate the signal, you can decide on the sampling frequency, you can decide on the averaging mode, on the type of window, and then you can see the amplitude spectrum, you can see the real and imaginary spectrum here. So, you could use this at home to understand more about the signal analysis, and the link through this is this website of iitnoise.com. Okay. Now, let us come back to this frequency domain analysis regarding modulation and sidebands, which I will focus mostly in this course here, rather in this lecture here. We had discussed about beats in the last class. Beating occurs when we have well, before I come to beats, I will tell you something about the harmonics and sidebands. For example, I have a frequency spectrum, I have certain amplitude. So, I have got a certain frequency, the first frequency. This is the fundamental. Okay. So, this is at a function of say x, I am writing this as x, and usually people write it as 1 x in the literature of condition monitoring. It may so happen this signal, and this is one type of signal, there could be spectrums peaks which are equally spaced, and this is an exact multiple of the value here. Okay. So, these are known as the harmonics. Okay. This helps us to know whether these harmonics are multiple of the fundamental. Suppose this value is, for example, if this corresponds to 20 hertz. Okay. So, if I see a value at a peak at 40, a peak at 60, a peak at 80, a peak at 100, I know that these frequencies are the harmonics. What happens? This is a very ideal situation. In the real one, once you go to the FFT analyzers, you will see that there will be a lot of noise like this buried, okay, and these harmonics are perhaps buried in the FFT. So, to our naked eyes, sometimes it becomes very difficult to determine what the harmonics are. So, sometimes there are what is known as the options are available, which are known as harmonic cursors. So, once you set at the fundamental a cursor which happens to be the harmonic cursor, automatically it will calculate, because it knows this distance or it knows this value. So, it will calculate and put the harmonic cursors at all the places in the spectrum, and then you can very easily identify if there is a peak, well, these are the harmonics, and so on. Okay. So, this is what is known as the harmonics, and harmonics occur because of particularly in unbalance and misalignment, you will see lot of such things occur. They are all multiples of vibrations. Okay. Then we have what is known as sidebands. Sidebands occur in the frequency spectrum around a particular frequency. For example, I have a peak here. I will also notice that there are two very prominent peaks almost equally spaced about, this is usually known as the carrier frequency. And this is the left sideband and this is the right sideband. Okay. And this value is the value of the what is known as the modulating frequency. So, the modulating frequency value was Fm, and this is Fc. So, the value here left sideband will be Fc minus Fm, and here it will be Fc plus Fm. Okay. Now, there could be sometimes Fc minus twice of Fm, Fc plus twice of Fm. So, basically there will be a group of sidebands around a carrier frequency. It would suffice right now to say particularly this kind of signals occur in speech signals, occur in gearboxes. Okay. Now, these are very ideally represented signals. If you go to the real world machines, again there will be a lot of noise, okay. And on top of it there will be many carrier frequencies. On top of it, the frequencies could be smearing because of the effect of the loads or the speed fluctuations. So, and then once you do an FFT, you may not be getting a sharp frequency because of the frequency smearing. So, because our objective is to identify frequencies. I mean, we should, why are we studying signal processing? Our primary objective is to identify frequencies, so that we can do fault detection. Okay. This is our primary objective. We should never forget that no matter what amount of signal processing we do, it may be a mathematical exercise altogether, but end of the day unless I detect the faults, my signal processing is no good. Okay. But so, what are the tools available? Excuse me. Excuse me. So, what are the tools available to do this kind of signal processing? We will come to this in the later classes regarding substrum analysis, wherein we can identify the sidebands, etc. But it would suffice to say that in a frequency spectrum, I will be seeing sidebands as well as harmonics, okay, or I may see none of them also at times. So, now let us see why and how these sidebands are generated in the first place and harmonics are generated in the first place. Okay. To begin with, let us talk about signal beating. Okay. For example, I have a machine A running at say 1200 RPM, that corresponds to 1200 by 60, that is 20 hertz. Okay. Some machine is there, it is operating and running. I have another machine B, which is for some reason it had a defective supply or something, it is running at 21 hertz. Okay. Of course, I am standing here. Okay. Now, because it is running at 20 hertz and this is a heavy mechanical machinery, it is also going to generate noise at these frequencies. To my ear, I am getting 20 hertz and also I am getting 21 hertz. Okay. And then you know, if I have two signals, say A 1 is equal to sin omega 1 t plus A 2 equal to sin omega 2 t, where omega 1 is equal to 2 pi f 1. So, in one case f 1 is equal to 20 hertz, in another case f 2 is equal to 21 hertz. Okay. So, once I see this or hear this signal, in fact, if you mathematically sum this signal, they are going to look like this. Of course, I am not being accurate while drawing in by my hand. This is how it will look in the time domain, and if I can draw a waveform, this is the envelope as it is known as, and this is the resultant signal A. So, you see this resultant signal which I hear is no longer constant in amplitude, it is changing with frequency, and this resultant frequency will be because of f 1 minus f 2 and f 1 plus f 2. Okay. So, two independent frequencies, because the relationship between machine A and machine B, they are totally independent, but the net effect produces a resultant signal something like this, wherein the frequency, then this signal will sound like as if you must have gone to a factory wherein two machines are running, and you will get this kind of howling noise, suddenly noise increasing, decreasing, increasing, decreasing, and that is because two machines are running side by side at very similar, very close by frequencies. So, frequency of this beating is nothing but f 1 minus f 2, and this is a very small quantity, and the time period of this beating is the inverse of this. So, in the frequency domain, all I will have is two frequencies close by, one is maybe f 2, one is f 1, certain amplitudes. I will not know whether they are beating unless I see the resultant waveform in the time domain. Okay. But I will see two distinct frequencies. Okay. And I will also see frequencies of f 1 minus f 2 and f 1 plus f 2. If I see this, I will know the signals are beating. Okay. But another very important characteristics of signal or types of signal is the signal modulation. Okay. Now, suppose I have a signal x t is equal to a sin omega t. Now, this a itself in this case is a constant, but suppose a was also varying with a frequency, a is given by a m sin omega m t, and this I will write as omega c. Okay. So, my x t will be a m sin omega m t sin omega c t. Okay. So, product of two sine functions will be a summation. You will have components in the resultant as two frequencies, one with omega c plus omega m and another with omega c minus omega m. So, the product of two sine waves, one is modulating the other, like I give an example of a very common example is ceiling fan. ceiling fan, the hub rotates at a particular RPM, say n RPM, the rotation of the hub, and then I have say number of blades is equal to 3. I will have the blade pass frequency as 3n by 60 hertz. So, you see the rotational speed of the ceiling, the blade pass frequency and the rotational frequency, they are related. One is affecting the other, and then we can have modulations to begin with. But modulations you will see in details when we talk about defects in ball bearings, in gears and so on. So, but the fact that x t is equal to a m sin omega m t times sin omega c t, this gives rise to omega c plus minus omega m, and this is what is the sidebands. If you look at this FFT of this signal, because modulation has occurred, the resultant waveform will have signals which will have frequencies of omega c plus minus f m, omega c plus minus omega m, or f c plus minus omega f m, and this is known as the carrier frequency, and this is known as the modulating frequency. I will so what are the features of this, distinguishing features of amplitude modulation? Suppose I have taken an amplitude modulated signal and I have done a fast Fourier transform of such a signal. One is I will see the carrier frequency f c, I will see the modulating frequency, but most important is I will see the sum of the carrier and modulating frequencies, difference of the carrier and modulating frequencies. Okay. In the case of the beating, these frequencies may not be visible, carrier and modulating frequencies. There will be two independent frequencies showing up. It could be f 1 and f 2 very close by, and usually in amplitude modulation one is pretty high compared to the other, and then this sum and difference frequencies plus these two frequencies will be seen. Then you can know for sure that amplitude modulation has occurred. Okay. And once we go to gear, but because our objective again is how do I find out my carrier frequency and modulating frequencies, because once you do the, so for example, this is a typical modulating signal. I will show you how this becomes modulating, because if you look at this signal, this is in time domain, this is a signal A. So, this is my high frequency carrier signal. So, the transducer has collected the signal and it is sending to the receiver or the analyzer, and the information is actually this one here. This is the low frequency modulated signal. The machine's defect or machine's features are actually there in the blue signal. machine's characteristic frequency. Okay. If I do, so I have to find out a mathematical technique by which I can only obtain this low frequency modulated signals, because otherwise what happens once you go to the frequency domain, there will be so many frequencies, you will be kind of getting lost, which one is your modulating frequency, which one is your carrier frequency, which are the multiples of carrier frequency, etc. There will be sidebands. So, there are mathematical techniques which we will cover subsequently to how do we demodulation or sometimes known as envelope analysis. Okay. There are many ways to do demodulation and envelope analysis, like using a Hilbert transform, that is something we will discuss later on. And then this can be used to obtain this blue signal, the envelope of this modulated signal, and thus know more about the machinery. Okay. I should again tell you one thing, other than this virtual labs, I would also recommend that all of you use the MATLAB signal processing toolbox to generate waveform signal feature extraction both in time and frequency domain. And MATLAB is a software which is freely available in educational institutes as a floating open license. Students are can use them, or you can buy them and then use them. But some of the examples which I will be subsequently showing you could be from our virtual labs website on signal processing, and also some examples done on MATLAB. So, in MATLAB, if you use the help menu, you can know how to do signal amplitude modulation, frequency modulation, how to feature out, find out the sidebands, etc. All these functions are available in the MATLAB. Now, another type of signal modulation is what is known as the frequency modulation. In frequency modulation, what happens, or AFM, I am writing AFM, A naught sin omega mt plus cosine omega ct . Okay. Now, in such a case, what happens if I was to draw this signal in time domain? The distinguishing features of frequency domain signal in the time domain is the amplitudes are constant, but the frequencies will vary. So, there will be an increase and decrease of the frequency about the same amplitudes, okay. Because you can see these are the high frequency signals, these are the low frequency signals, because the time period has changed and then amplitudes are constant. Such signals also we will come across in machinery and then we will see some of the features of this in the signal processing. Now, what are the distinguishing features of the frequency modulated signals? Carrier frequency at the center of component array. You will see a lot of sidebands. Okay. And the presence of a multiple sidebands with a spacing of FC minus FM or FC plus FM, some x times FM, this is plus, and this is again FC plus or minus some multiple of FM. And this actually occur in rotating shafts, and particularly when we are monitoring torsional vibrations as a function of the angular displacement. Okay. So, there will be multiple sidebands at carrier frequency minus orders of the modulator, and multiple sidebands at the carrier frequency plus orders of the modulator, and constant signal amplitude when viewed in the time domain, which you would have seen, but there is no distinct component occurring specifically at the modulating frequencies, which was present in the case of amplitude modulated signals. So, you will not see this happening in the case of the frequency domain FM signals. Now, this AM and FM signals have traditionally been used in electronics, mostly for radar communication, wherein because the carrier frequencies are usually high frequency signals, and high frequency signals are very directive. Okay. For example, the radio signals, the TV signals, they are very high frequency signals, gigahertz, and very directional. So, if you have an antenna, you must have observed that when an antenna, particularly with your shortwave radios or AM radios, you have to point the antenna towards the source, and because these are high frequencies, they are very directional, and on this carrier high frequency carrier signals, my information signal is the information signal. It could be a radio station signal, TV, it could be machinery. Okay, these people talk in the order of gigahertz, I am talking in the order of only hertz or kilohertz. Okay. Our signals are of much lower bandwidth than the radio signals, but nevertheless the physics of data communication is the same, the laws are the same, but objective again from a machinery condition monitoring point of view, how do I get this information, whether it is frequency modulated or amplitude modulated is immaterial to me, as long as by some signal processing algorithm I can find out this information, green information signal. Okay. And that is what we will discuss in the subsequent classes regarding how do I find out the harmonics, how do I find out the sidebands, most importantly how do I find out the modulated signals from such composite signals. And mind you, once you go to the frequency spectrum of a signal, because see, my machine is there, my machine is an inanimate object, and many things are happening in it simultaneously. All I have is put this poor transducer. Okay. So, everything depends on what my transducer is capturing. So, the phenomena of resonance could be occurring, the phenomena of modulation could be occurring, okay, everything, and of course, our good friend noise is always present. Okay. So, everything is happening together in this system, and I only capture this by a transducer, and transducer is, no matter what you see in an oscilloscope, will always give me signal which is, I can make nothing out of it. Okay. Our starting point in CBM is this. I will not get a signal, a transducer will never tell this is your modulated signal, this is your resonance signal, this is your noise signal. No, everything is there built in, summation, sum effect of all signals are there. So, we have to now use our skills, mathematical power, how do I analyze such signals. First of all is whether it is a stationary signal, whether it is a non-stationary signal, whether I can find out features in the time domain which are repeatability of the signals, or whether it is one of a kind. Then we have to go into the frequency domain, see if my FFT, I can see the frequencies as sharp peaks or there are no frequency smearing, this is to be avoided. Now, on top of it, if signals are getting modulated, there are presence of lot of sidebands, and at the end of the day I will land up with a signal wherein a lot of these components are there. So, then we will see how we can analyze the signals to get the different frequency content of the signal. Okay. So, I think with this I will stop here. Thank you.